Okay, active filters. So we have all our passive components, R's, L's, and C's we can do stuff with. The gain, they're passive. You can't get greater than one gain. And inductance can make them difficult to handle. Inductors are kind of big and bulky and stuff like that. So we can use operational amplifiers to do these things with resistors and capacitors. Okay. So now here's the operational amplifier model in terms of dependent sources. Most of the time people use the ideal. They don't go to the real model. The ideal is so close to reality. The tolerance on components is going to be bigger than any kind of errors due to an op-amp being a little bit off. Okay, so now we use impedances instead of resistors in our feedback loop. And this is the inverting. Remember, Z2 over Z1 times V1 equals V out. And there it is right there. So now we can change what Z1 and Z2 are to get the gains we want. Here's a basic low pass filter that it looks a lot like the R1 and R2 look like a standard, the op amp with resistors. As soon as we put the capacitor in at high frequencies, this impedance is going to go down. So we can analyze it. Z2 is that. Z2 over Z1 is going to be the gain. And voila, you have it. Oops. You have your low pass. Let me go back a second. Yeah, when omega is small, you have a gain of R2 over R1. When omega is really big, the gain goes to 0. And you can draw the Bode plot, just like other things. So here's a similar configuration, except this time we're doing the non-inverting amplifier. The advantage of this, of course, is that V1 sees infinite resistance. The input voltage sees infinite resistance. In this case, it does not. So this has an advantage. Remember, we went into instrumentation amplifiers. We're using 3 op amps. So the impedance of both inputs is infinity. Okay, so now we analyze this and we get the equations just like we got before. This is what we got before. And here's using the non-inverting configuration. We take our formula and plug and chug. Z2 over Z1. And we get this. A 0. Oops. That is not a 0 because you have a division here, right here. V out equals one plus Z2, which is the feedback, yeah, just looking through it, just making sure we have that right. Z2, I'm going to write that down. Take a little time to do that. Equals, it's in parallel, so it's R 1 over J omega C. So this is a parallel combination, R plus 1 over J omega C. multiply Z2, multiply j omega c times the top and bottom. You have r divided by j omega c2, by the way, c2 r plus 1. Okay, which is that there, that's the denominator. So that's z2 in the numerator, excuse me, that's z2. z1, and then the 1 plus. Okay, so we get that going, do some simplification, and we got this. 1, 0, 1 root at 1 over tau 1 and 1 over tau 2. Tau 1 is bigger, so omega 1 is going to be small. Omega 2 is going to be big. And depending on the values, ratios, well, anyway, let's keep going. So what we're going to have is a Bode plot that looks like this. We don't have a negative 20 dB starting out because we don't have an omega times something, something, something. So zeros make it rise. Tau 1 is, omega 1 is smaller. So here we go, 1 over tau 1. We're going to have a rise right here. So it's going to be flat line, rise, flat line. Okay. Now, things get a little hairier. Math gets a little hairier. This, I'm not going to go through all the math. It's just very complicated. But here's the result. Second order. This is like an LRC circuit. The previous ones were like an LC circuit. You could, or an RC circuit. So this is like a first order, like a regular band high pass or a low pass filter. So that acts like this. Now this one here acts like an LRC, but now you don't have any L's floating around, and you can tune it. So here's your omega term. Okay, this is your quality term, 2 zeta. So we're just going through designs. We're not going through all the math. Let's see. This looks like a good place to stop. I'll pick up the transconductance amplifier later. It's like an op amp. Notice it looks a lot like an operational amplifier. I'm going to give you a heads up before I go to the next video. But you have V in goes to current out by this equation. Instead of voltage in, voltage out, you have voltage in, current out. That's why they call it transconductance amplifier. Stopping here, we'll pick up next time.